Chapter 9, Introduction to Hypothesis Testing. In this video, we'll learn how to formulate null and alternative hypotheses, as well as understand the difference between type 1 and type 2 errors. Hypothesis testing is an application of statistical inference, where we make a hypothesis about the population and then use sample data to see if it's true or not. So whereas in descriptive statistics, we take data and describe what's occurring, with inferential statistics, we're taking sample data to infer what's going on in the population, since we can't study everybody in the population. Hypothesis testing is performed in many industries, such as manufacturing, food, and pharmaceuticals. It is a major part of business statistics and will be the focus for the remainder of the semester. Hypothesis testing helps business professionals have a way to make decisions about the population means, proportions, as well as compare different populations, even though we don't have all the information about the entire population. In this chapter, we'll focus on means and proportions of single populations. In hypothesis testing, two hypotheses are formed. The null hypothesis, denoted by H sub 0, and the alternative hypothesis, H sub A. Now, the null hypothesis will always have the equality sign in it, whether it's equals, less than or equals, or greater than and equals. Our hypotheses are always stated in terms of the population mean because we are hypothesizing what's going on in the population. Again, this is because we can't study the entire population, so we'll use samples to understand it. We do not write hypotheses about samples because we have all the sample data. So you don't have to hypothesize. You would just analyze it like we do with descriptive statistics. When working with hypotheses, we assume that the null hypothesis is true. So we'll assume this first statement up here is true, and we'll only reject it if our sample data gives us enough evidence to contradict it. Having enough evidence means that our null hypothesis is not true, and therefore our alternative hypothesis holds true. This is similar to criminal cases, where we assume someone is innocent or not guilty until there's enough evidence provided beyond a reasonable doubt that they are guilty. So there are three common reasons to test a hypothesis in business. The first is to test the status quo, to see if everything is working fine or if something needs to be changed and fixed. So for instance, Kellogg's cereal wants to make sure its cereal boxes are filled with 16 ounces of cereal. If it fills too little, customers will be dissatisfied. So if you've ever opened up a cereal box and you see it's all air, you're like, is this really all the cereal I get? Or if the company overfills, then they're giving away extra cereal for free and they're likely losing money. So here, in red, our null hypothesis states that the mean fill of a cereal box is equal to 16 ounces. That means our machine is working. The alternative hypothesis states that the mean fill does not equal to 16 ounces. That means something's wrong with our machine. Now, not equaling 16 ounces, it could mean that it's overfilling or underfilling, but we don't necessarily know. We just know that the machine is not working as intended. Another purpose for hypothesis testing would be to test a research hypothesis. This is often related to new product development, where the decision maker wants to demonstrate something to be true. So for instance, Goodyear wants to be able to declare that its tires will last longer than 60,000 miles on average. This would show to customers that their tires last a long time. So in red here, we see that the research hypothesis is our alternative hypothesis because Goodyear has to find evidence to prove that this alternative hypothesis is true, whereas our null hypothesis states that Goodyear's tires last less than or equal to 60,000 miles. So one way to think about the research hypothesis is if the alternative hypothesis is true and the tires last greater than 60,000 miles, it's a win for the new product. Other times, companies want to test a claim. In our textbook, to be consistent, if the stated claim includes the equality in our story, it's going to be the null hypothesis. If it doesn't include the equality sign in the story, then it's going to be the alternative hypothesis. So for instance, here we have a medical clinic claims the wait time is less than 15 minutes. So less than 15 minutes in its statement does not include the equality sign. Therefore, this is going to be our alternative hypothesis. The medical clinic is going to want to test if this claim is true. And this is relevant because we don't want people waiting too long in a clinic and their condition worsening or being frustrated at long wait times. So within hypothesis testing, there are a few types you'll commonly see. The first is a two-tailed test. This is a test where our null hypothesis will be rejected if the sample mean that we found is much larger or much smaller than our hypothesized population mean. So recall in Chapter 8, we learned about confidence intervals where we were looking at our data typically falls within this space, whether it's 80%, 90%, or 95%. With hypothesis testing, we're now focused on the outer tails, where our sample mean is either extremely larger or extremely smaller. And therefore, we're now out in the tails. That means it's not within our confidence interval estimate in here. A one-tailed upper test is where we're testing to see if the null hypothesis will be rejected if our sample mean is much larger than our hypothesized population mean. So with a one-tailed upper tail test, we can see now that if my sample mean is so much larger than our hypothesized mean, it's going to be on the right tail over here. Similarly, you could also be working with a one-tailed lower test where we're testing to see if our null hypothesis will be rejected if our sample mean is much smaller than the hypothesized population mean. So here we can see if my sample mean is much smaller than my hypothesized mean, I'm going to be on this tail, and we would reject the null. In other words, if our sample mean is somewhere in here, in any of these shapes, we do not reject the null, meaning our null is true. That first statement on top is true. If our sample data gives us enough evidence that we're way out in one of the tails, either on either end in a two-tailed test, or in the upper right tail in a greater than test, or in the left-hand lower tail in a less than test, then our null is not true and our alternative hypothesis is true. Let's look at an example. The mayor of Oceanside claims that the mean or average time spent by people in metered parking spaces at the beach exceeds 33 minutes. This is useful to know because decisions can be made about how much time to allow people to park at meters, how much to charge, if we need to have more parking attendants to check the meters. Because the claim states exceeds 33 minutes, that implies greater than, and this will be our alternative hypothesis. So if we took a sample of 50 cars at the beach to test this hypothesis, and if it turns out the average time those 50 cars is much larger than our hypothesized mean, in this case our hypothesis is 33 minutes, then that means our sample mean is somewhere here in the upper tail. So we would reject the null and see that the mayor's claim is true, that yes, people do park more than 33 minutes at the beach. And then we can make some adjustments to the meter situation. What if it's a one-tailed lower test? Say the Department of Agriculture has stated that the average annual rainfall in California is at least 23 inches to not be considered in a drought. And, in California, we are a drought-prone state. We could use hypothesis testing to determine if we're in a drought or not. So at least means that it includes 23 or more inches of rain. And recall, null hypotheses have to have the equal sign in it. So our statement belongs in the null hypothesis because it says at least, meaning 23 or more. So in this case, if we took sample data from rain collected throughout the state, and the sample mean is much lower, meaning say we have a sample mean of 20 inches of rain. So low, after we account for sampling error, that it's somewhere here in this lower tail, then we will reject the null, and it turns out we do have a drought year because our alternative hypothesis, which states the average rainfall is less than 23 inches, is true. For a two-tailed test, let's look at this example. Say the bottling company that bottles Coca-Cola has its filling machine set to 12 ounces per bottle. Again, in this instance, it's important that we don't want to underfill or overfill the bottle. Underfilling results in unhappy customers, and overfilling means we're wasting soda and maybe even spilling over the bottles and causing a potential accident on the manufacturing floor. So taking a sample of bottles and testing how many ounces are in the bottles, if the sample mean is found to be much larger or much smaller, so much larger, meaning our sample mean falls out here, or much smaller, so our sample mean falls over here, thus falling in either tail, we reject the null and would need to fix the machine. If our sample mean falls within here, we would not reject the null and know that the machine is working fine. So just think of hypothesis testing as a visual where we're now testing our sample mean against our hypothesized population mean. And we're trying to see, is it within my null hypothesis, or is it so far away that it's going to be rejected, either because it's too big or too small. Here are the possible outcomes of hypothesis testing. Recall in Chapter 7, we learned about sampling error, where our sample is never going to be a perfect number to match our population parameter. So because of the potential for extreme sampling error, two possible errors can occur when a hypothesis is tested. We might have a type 1 error or a type 2 error. So in this table here, it shows the states of nature on top. In other words, the null hypothesis could be true or the null hypothesis could be false. And here on the left, we have the decision based on our sample data that our business decision makers will choose. So our business decision makers would either not reject the null or reject the null. If our null hypothesis is true, but we reject the null, a type 1 error has been made. If the null hypothesis is false, but we do not reject the null, then we've made a type 2 error. In this class, we will focus on type 1 errors, which is when the sample data leads us to reject the null when it is actually true, because the decision maker controls or chooses our alpha level. How much error are we willing to accept? Whereas type 2 error, the sample data leads us to not reject the null when it is false. A visual might be a little easier to understand type 1 and type 2 errors. So imagine our hypothesis test states that for the null, you're either not pregnant or the alternative, you are pregnant. Imagine you go to the doctors and are given a pregnancy test. Here we have a type 1 error where the doctor is telling this gentleman that he is pregnant. This is considered a false positive. So somehow the evidence is showing that this patient is pregnant, but we know that's not possible. For a type 2 error, this is where the doctor is telling this woman that she's not pregnant, despite visibly showing a baby bump. This would be considered a false negative. So somehow the test incorrectly is telling us that she's not pregnant. And that's why many statisticians argue that you should never use the phrase accept the null hypothesis. Instead, we'll say we do not reject the null hypothesis. Thus, the only two hypothesis testing decisions would be either reject or not reject, because we recognize that there's a chance that there might be an error. That's why with verdicts, juries will say not guilty rather than innocent, because in reality, the person may not be innocent. The same is true with the hypothesis testing. Just because the sample data does not lead to us rejecting the null hypothesis doesn't mean the null hypothesis is true. So in other words, this is one way to protect yourself where you recognize that there's a chance for error and you're highlighting the fact that the sample data is where you're making your decision from. And there's a chance that it might be wrong. The next video will walk you through how to conduct a hypothesis test.